Motion in space, part 2. Let r be the position function of an object. Let's find the magnitude of r. We use the magnitude formula, and we find that the magnitude of r is equal to 5 for all values of t. Since the position function has a constant magnitude of 5, we know that the object is always 5 units from the origin. Let's find the dot product of r with v. First we find the velocity vector and then set up the dot product. And we discover that the dot product is equal to 0. Since the dot product is equal to 0, we know that the position function is orthogonal to the velocity function. Now recall that we said that r has a constant magnitude of 5. We saw that scenario in part 1. And in fact, it is always true that when the magnitude of the position function is constant, the position vector and the velocity vector are orthogonal at all times. Here we have a small projectile being fired over horizontal ground in an easterly direction, an initial speed of 300 meters per second, an angle of 30 degrees above the horizontal. We have a crosswind blowing from north to south. Now, where does the projectile land? For this problem, we will use the positive x-axis to indicate east, the positive y-axis to indicate north, and the positive z-axis to represent up. And we will first focus on the crosswind. The crosswind blows from north to south, producing an acceleration of 0.36 meters per second to the north. Combining the acceleration due to the crosswind together with the acceleration due to gravity, we find the overall acceleration vector. Next, find the velocity vector. We find the antiderivative of the acceleration vector, and then to determine the constant vector c, we determine the initial velocity v of 0. The projectile is fired in an easterly direction with an initial speed of 300 meters per second at an angle of 30 degrees above the horizontal. So the initial velocity is 300 cosine 30 for the easterly component and 300 sine 30 for the vertical component. Since it's fired in an easterly direction, there is no y component. I mean, the y component is 0, is what I mean. So v of 0 is 150 radical 3, 0, 150. We use that to go back and find our velocity vector. Our next step is to determine the position vector. Again, we find the antiderivative and then think about the initial position of the object. Since the initial position is 0, 0, 0, our constant vector is just 0, 0, 0. When does the object land? The projectile will land when the z component is 0. So we set the z component equal to 0, and we say after time of 0, when does it again reach a vertical height of 0? After we find the time at which the projectile lands, we put that value of t back into our position vector. Now the z component will be 0, but what is the x and y component? And we find that the object lands 7,953 meters east and 169 meters north. In order to correct for the crosswind and make the projectile land due east of the launch site, at what angle from due east must the projectile be fired? Now we're going to assume the same horizontal angle of 30 degrees. The same angle from the horizontal of 30 degrees and the same initial speed. So in terms of being tipped up from the ground, that angle is the same. But now we want to pivot it slightly. Since the projectile is fired with an initial speed of 300 meters per second at an angle of 30 degrees above the horizontal, the initial vertical velocity is 150 meters per second. That's the same. And the initial horizontal velocity, 150 radical 3, that is the same as well. However, we now want to distribute that initial horizontal speed. Let theta be the angle relative to due east that we need. We want to distribute the initial horizontal speed into an east and now north component such that we land due east. Notice that the north component will likely be negative. We're going to want to point slightly south because of the crosswind. With an initial velocity of 150 radical 3, the east component of that will be 150 radical 3 cosine of theta, and the north component will be 150 radical 3 sine theta. In summary, the vertical component of the initial velocity is 150. The east component is 150 radical 3 cosine theta, and the north component is 150 radical 3 sine theta. The acceleration has not changed, and we are now ready to find the new position function. We find the antiderivative of acceleration and use the initial velocity to find c. Then we simplify. After we simplify, we find the position function using that the initial position is 0, 0, 0. At what time will the object strike the ground? The object will strike the ground when the z component is equal to 0. Again, we find that if the z component is equal to 0, then t is either 0 or 150 divided by 4.9. The goal now is to choose theta such that the north component, y, is equal to 0. So for y, we put in 150 divided by 4.9, and we set that equal to 0. When it strikes the ground, we want y to be 0. And what will theta have to be in that situation? So the rest is solving for theta. So of course we want to isolate sine of theta, and then we use arc sine, and we get approximately negative 1.22 degrees, so just a little bit south of due east. So the object should be launched about 1.22 degrees south of east to correct for the northerly crosswind. Take care, and I'll see you again in 12.8.